In our equations, we often have some information about the physical state of each of the reactants and products. We can put an S for solid, L for liquid, G for gas, or AQ for aqueous, meaning dissolved in water. For example, we can see the states of matter listed in the equation. 2 sodium solids react with 2 liquid waters to make 2 aqueous sodium hydroxides and 2 hydrogen gas. That actually tells us a lot of information about the things that are going into the reaction and coming out of it. We would be taking a solid and mixing it with a liquid, let's say in a beaker, and then we get an aqueous solution where the solid's dissolved, and some hydrogen gas is going to be coming out of the beaker. You can start getting a mental picture of what this would look like when you actually do it in the lab. Additionally, if we see a delta symbol on top of an arrow, that means that the reaction is heated in order for the reaction to happen. Calcium carbonate can be heated up in order to decompose it into calcium oxide and carbon dioxide. When we have equations involving ionic compounds, we can write them 3 different ways. Our first way is as a molecular equation, in which we're treating ionic compounds as if they were molecules that stay stuck together. In reality, when we put an ionic compound into water, it's often going to break apart into ions as it dissolves. If an ionic compound dissolves when it is put into water, we put the AQ symbol next to it. Again, AQ means aqueous or dissolved in water. Notice the AQ symbols after the calcium chloride, silver nitrate, and calcium nitrate in the equation on this slide. If the ionic compound does not dissolve when put into water, it's going to stay as a solid, clumped together. So we put an S next to it for solid. Notice the S next to silver chloride on this slide. The second way to write ionic equations is as a complete ionic equation. A complete ionic equation represents the ions the way they really are in the solution, that is, as individual ions. Anything that is both ionic and aqueous breaks up into individual ions, and we write it that way. Instead of writing the CaCl2 together, we're going to write it as 1 calcium ion and 2 fluoride ions. The calcium ion has a +2 charge because calcium is in group 2A. The chloride ion is a -1 because chlorine's in group 7A. There are 2 chloride ions, which is why there's a subscript of 2 in the chemical formula. That subscript of 2 becomes a coefficient of 2 when we write it as an individual ion. Remember, subscripts indicate something is bonding together, whereas coefficients indicate separate items. If we write it as CaCl2, that's telling us that the calcium and the chlorines are stuck together. Instead, on the right side, when we're writing it as individual ions, the chlorine is represented with a coefficient of 2 to tell us that we've got 2 chloride ions that are separate from each other. Our next aqueous substance in this reaction is 2 silver nitrates. So it dissolves to make 2 silver ions and 2 nitrate ions. We know the charge on the nitrate ion is a -1 because we've memorized our polyatomic ions. We know the silver has a +1 charge based on the fact that it's bonding to 1 nitrate. Remember, ionic compounds must be neutral overall, so the silver must be a +1 charge to balance out the -1 charge on the nitrate. The coefficient of 2 in front of the silver nitrate ends up being a coefficient of 2 in front of each of the resulting ions. The final aqueous ionic compound in this reaction is calcium nitrate. It breaks apart into 1 calcium ion with a +2 charge and 2 nitrate ions, each with a -1 charge. The subscript of 2 in calcium nitrate is telling us how many nitrate ions are in the formula unit. The subscript of 2 only applies to the nitrates. It does not apply to the number of calcium ions. The 2 silver chloride solids do not dissolve in water. We write them as is in the complete ionic equation. If it's a solid, liquid, or gas, we leave it alone. We do not break it apart into ions. We end up with a complete ionic equation of Ca2 plus 2Cl minus plus 2Ag plus 2NO3 minus makes Ca2 plus 2NO3 minus plus 2AgCl solid. Each of the ions should continue having the AQ symbol written after it, and that solid symbol after the silver chloride is super important. It is also really important that you include the charge on all ions. Ca is very different from Ca2+. It is chemically wrong to leave off the charge from an ion and will be counted against you. I've mentioned a few of these, but here are some tips for writing your complete ionic equations. If there's a coefficient in front of the compound, it applies to all of the ions within that compound. For example, the 2 in front of the silver nitrate applies to both the silver ions and the nitrate ions that result from it. If there is a subscript in a compound that's not part of the formula of a polyatomic ion, when we write it as ions, the subscript becomes a coefficient. Writing it as a coefficient indicates that the ions are separate from each other and not bound together. We're only breaking apart things that are ionic and have the AQ symbol next to them. If the compound is covalent, we're not going to break it apart. And if it is a solid, liquid, or gas, we're not going to break it apart. Our last type of equation is called a net ionic equation. In this type of equation, we're showing which things are actually involved in the reaction. Some of the ions in a reaction are typically going to be there just to balance out charges, and they will appear on both sides of the equation. These ions are called spectator ions. They're like the spectators at a football game. They're just there to watch, not to play the game. Spectator ions don't participate in the reaction. We can find the spectator ions by looking for the things that appear on both sides. In this equation, we have calcium ions on both sides, and we have 2 nitrate ions on each side, so we can cross them out. Everything that's left is going to make up the net ionic equation, the things that are actually doing the reacting. In this case, we've got 2 chloride ions and 2 silver ions on the left, reacting together to make 2 silver chloride solids on the right. It will often be the case where we have some ions coming together on the left, and they are the ions necessary to make the solid ionic compound on the right-hand side. Here are some tips for writing net ionic equations. First of all, if your molecular equation is balanced, then your complete ionic equation will also be balanced, and your net ionic equation will also be balanced. If your net ionic equation is not balancing, go back and check your other equations to make sure that they were balanced to begin with. Also, we can typically look for the things that are ionic and aqueous on the right-hand side, and they will often cancel out. They'll often be the spectator ions. In this equation, we've got calcium and nitrate on the right, and we look on the left and see, yes, those also appear on the left, so we can cancel them out. If we were just looking at the left first, we would have 4 ions to look for. But if we look for the ions on the right side first, we only have to look at 2. That can save you a few extra seconds on the exam. Finally, if we get an equation where the coefficients can cancel out or simplify, then we're going to do that. In this case, we got 2 in front of each of our substances. So we divide each of those coefficients by 2, and they become 1s. We end up with just chloride plus silver ion makes silver chloride solid. Here's an example where not everything in the reaction is ionic. Again, everything in this equation is in word form first. So you're going to have to take that word form and turn it into the chemical formulas in order to know what the reaction is and manipulate it. We have carbon dioxide reacting with sodium hydroxide to make sodium carbonate and water. Our first step is to write out that full equation. Carbon dioxide is CO2, sodium hydroxide is NaOH. Remember, hydroxide has a -1 charge, so we need 1 + 1 sodium to go with it. Sodium carbonate is Na2CO3. Remember, carbonate has a -2 charge, so we need 2 + 1 sodiums to go along with it. Liquid water is our last substance, and that's H2O. Right now, we haven't really worried about balancing the equation. We just wrote down the identities of the things in the reaction based on the word problem, making sure the ionic compounds were neutrally charged. Now we're going to take that unbalanced equation and balance it. Our first step is writing down the numbers of each thing we have on each side of the equation. On our left, we've got 1 carbon, 3 oxygens, 1 sodium, and 1 hydrogen. On our right, we have 1 carbon, 4 oxygens, 2 sodiums, and 2 hydrogens. Right now, the carbon is balanced, but the other 3 are not. It turns out sodium hydroxide has sodium, oxygen, and hydrogen, which are the 3 things that are not balanced. That means all we have to do is put a number in front of the sodium hydroxide to make the rest of it balance. That number ends up being a 2. That gives us a total of 4 oxygens on the left, 2 from the CO2 and 2 from the sodium hydroxide. We also now have 2 sodiums and 2 hydrogens from the sodium hydroxide. The balanced equation becomes carbon dioxide plus 2 sodium hydroxide makes sodium carbonate and water. Now that we have our balanced molecular equation, we can turn it into a complete ionic equation by taking everything that's both ionic and aqueous and breaking it apart into ions. The CO2 is aqueous, but it's not ionic, so we're not going to break it apart. It is covalent or molecular, so we leave it alone. The sodium hydroxide is ionic and aqueous, so we are going to break it apart. Since we have 2 sodium hydroxides in our balanced equation, we break it apart into 2 sodium ions, each with a +1 charge, and 2 hydroxide ions, each with a -1 charge. Sodium carbonate is also ionic and aqueous. We break it apart into 2 sodium ions, each with a +1 charge, and 1 carbonate ion, which has a -2 charge. Finally, we have the water molecule, which is both molecular and liquid, so we have 2 reasons not to break it apart. We finally write our net ionic equation by canceling out spectator ions. We are going to cross off the sodium ions, which appear on both sides. And everything that's left is going to be in our net ionic equation. Our final net ionic equation becomes CO2 aqueous plus 2 hydroxide aqueous makes CO3 2- aqueous and water liquid. What is the net ionic equation for the reaction between sodium chloride and silver nitrate? NaCl aqueous plus AgNO3 aqueous makes NaNO3 aqueous plus AgCl solid. Is the answer A, Ag plus aqueous plus Cl minus aqueous makes AgCl solid? B, NaCl aqueous makes Na plus aqueous plus Cl minus aqueous? C, Ag plus aqueous makes Ag solid? Or D, Na plus aqueous plus NO3 minus aqueous makes NaNO3 aqueous? The correct answer is A. Ag plus aqueous plus Cl minus aqueous makes AgCl solid. When we write our complete ionic equation, the sodium chloride gets broken apart into ions. The silver nitrate gets broken apart into ions. The sodium nitrate gets broken apart into ions, and the silver chloride solid stays as is. It turns out the sodium ions and the nitrate ions end up on both sides, so they cancel each other out. We're left with the chloride ion and the silver ion on the left, and the silver chloride solid on the right. This is going to be the case pretty often, where we have ions on the left that can come together to make the solid ionic compound on the right.